Hi folks, today I am excited to be talking through a proof that sort of concludes what we're going to study on Euclidean domains. So specifically we're going to look at this theorem that says the Euclidean algorithm works in a general Euclidean domain setting. So this is really exciting, I think. We're saying that if R is a Euclidean domain and A and B are two non-zero elements of R, then applying the Euclidean algorithm, right, which consists of doing these repeated quotient and remainder calculations, if we take the last non-zero remainder in the Euclidean algorithm for A and B, then the result, that last non-zero remainder, is the greatest common divisor of A and B, and the principal ideal generated by that last non-zero remainder is exactly the ideal generated by A and B, and it follows from that we can write that last non-zero remainder, the greatest common divisor, we can write that as an R linear combination of A and B. So we're translating these powerful tools from the integers into this general Euclidean domain ring theoretic context. So our proof starts with two non-zero elements in a general Euclidean domain R. We'll call these elements A and B. We've already proved two propositions that sort of set the stage for this result. The first, in our discussion on divisibility and greatest common divisors, we showed that if two elements A and B generate some principal ideal, and we figure out what that one generator is for the principal ideal, that generator is necessarily the greatest common divisor of A and B. This came in sort of translating the definition of greatest common divisor into the language of ideals. And furthermore, we showed that every ideal is principal in a Euclidean domain. So we are starting this out with the knowledge that A and B will generate a principal ideal, and that generator, the principal generator for that ideal, is the GCD of A and B. Our mission then is to show that that aligns with the result of the Euclidean algorithm. So let's say D is that principal generator, then our goal in this context is just to show that D is equal to Rn, where Rn is that last non-zero remainder in the Euclidean algorithm. Specifically, we're going to show that Rn divides A and divides B. This implies that the ideal generated by the ideal generated by A and B is contained in the ideal generated by that Rn. And we're going to show that we can write this Rn term as a linear combination, an R linear combination of A and B, which gets us the reverse containment, and then we know we've found the right generator. So let's get to it. To prove this divisibility, we're going to induct down through the indices of the terms in the Euclidean algorithm. So starting at the bottom, we see that since Rn is the last non-zero remainder, Rn must divide Rn minus 1, and, trivially, Rn divides itself. So then our induction hypothesis will assume that Rn divides successive terms, Rk plus 1 and Rk, and look at the formulation for Rk minus 1. So Rk minus 1 is Qk plus 1 times Rk plus Rk plus 1, right? To find that successive quotient, we're looking at it in terms of the previous remainder and finding the next remainder, but we're inducting down, right? And so by representing R sub k minus 1 in terms of Rk and Rk plus 1, hey, we must, Rk minus 1 must be divisible by Rn, since both terms in the sum on the right-hand side are divisible by Rn by assumption. So by induction, right, we've shown a base case that is the Rn step, and we've shown that we can get from the k case to the k-1 case. So every single one of those quantities expressed on the left-hand side of the equal sign in the Euclidean algorithm must be divisible by Rn, and just sort of working our way up from the bottom, right? R0, the term before that is B, the term before that is A, and so Rn divides each of those quantities, including A and B. If you wanted to, you can think of those like R sub -1 and R sub -2, right? They play the role of that remainder being expressed through this division algorithm. So we've done it. We've shown the first implication. Check. And at last, to approach the other direction of this implication, we'll induct in a more traditional way, starting with indices of 0 and 1 and building up to index n. So we're just going to rearrange the very first equation that our Euclidean algorithm gets us and see that, oh, I can write R0 as this linear combination of A and B. That is A minus my quotient Q0 times B, which means R0 is in the ideal generated by A and B. This, in turn, implies, doing the same rearrangement, that R1 equal to B minus Q1 times R0. Well, it's a linear combination of B and R0, so that's in the ideal generated by B and R0, but R0's a member of the ideal generated by A and B, and so that ideal is contained in the previously established ideal. Okay, so R1 must be in the ideal generated by A and B, since it's made up out of things that are in the ideal generated by A and B. So, proceeding by induction, our induction hypothesis here is that the k-1st and the kth remainder are in the ideal A and B. We can rearrange that k plus first equation to see that rk plus 1 is equal to rk minus 1 minus qk plus 1 times rk. Okay, just doing the same arrangement we did before, rewriting that new remainder, the k plus first remainder, in terms of the previous remainders, and we see, oh yeah, it's a linear combination of the previous remainders. It's in the ideal generated by rk and rk minus 1, but our induction hypothesis is that those two elements are in the ideal generated by A and B, and so that ideal is a subset of the ideal generated by A and B. Hence, rk plus 1 is in the ideal generated by A and B. So we successfully made it from an assumption about the k and k minus first terms, proved that it's true then, consequently, for that k plus first term. Hence, our induction holds, and Rn is in the ideal generated by A and B, whatever that index n may be. Our last non-zero term also satisfies the same property. And that proves our theorem. Since we showed that the ideal generated by A and B is contained in the ideals generated by Rn, and vice versa, we get to conclude that Rn is a greatest common divisor of A and B, which, throwback, another theorem that we proved in class, means that Rn only differs by a unit. It's scalar scales up to a unit to any other GCD of A and B, so they all, whatever GCD you pick, generates the same ideal, and therefore there exists these coefficients xy in R, so that we can write Rn as ax plus by, since that's what it means for Rn to be in the ideal generated by A and B. Thanks, folks. Let me know if you've got questions. I hope this is helpful.